Cram is a turn-based game played by two players on a gridded board of an arbitrary size. On each turn, a player can only place one piece horizontally or vertically on the board, which occupies two grid squares. Pieces are not allowed to overlap. The aim of the game is to be the last player to play a piece, leaving the opponent with no possible move. One of the better known winning strategies for Cram is known as symmetric play. In this strategy, one player copies the other player's moves in order to win the game. This strategy applies on even by even boards, as well as even by odd boards. On even by even boards, the second player will always win by symmetric play, as there is always a symmetric move for any move that the first player plays. On even by odd boards, the first player always wins. This is because even by odd boards have one unique position with no symmetric equivalent, and that is the center of the board. By placing his piece in the center of the board, the first player forces the second player to play the first asymmetric move. From this point on, there will always be a symmetric move for any move that the second player plays. The proof for this is as follows.
Area 4.
As we have seen, symmetric play is a simple winning strategy that easily wins a game of Cram, and makes the game's outcome easily predictable even before the first piece is placed. However, it does not apply to odd by odd boards. Do winning strategies exist for odd by odd boards? What if the players choose to play asymmetrically? Does a winning strategy still exist? In order to answer these questions, we explore a theorem in combinatorial game theory called Sprague-Grundy theorem. Sprague-Grundy theorem is a theorem that applies to all impartial games. An impartial game is one in which the possible moves is independent of which player's turn it is, and only dependent on the current state of the game. Either player has the same set of possible moves from any given game state. Sprague-Grundy theorem states that all impartial games can be reduced to a game of nim. It also states that all game states of impartial games have a Grundy value. The Grundy value of a game state is defined recursively as the minimum excluded value of the Grundy values of all possible game states that can be reached within the next move. This recursion ends on the base case that a game state with no moves left has a Grundy value of 0. The minimum excluded value of any set of positive integers is the smallest positive integer that is not an element of the set. A 0 minimum excluded value implies that 0 is not an element of the set. A non-zero minimum excluded value implies that 0 is an element of the set. Based on the definition of the Grundy value, it follows that the Grundy value of a game state will be non-zero for the previous game state before the last piece was played, 0 for all the game states that can only lead to non-zero game states, non-zero for all game states that possibly lead to zero value game states. A non-zero value game state implies that there exists a move with a Grundy value of 0. If there is a game-ending move in this game state, this move is the winning move. A zero value game state implies that there are no moves with a Grundy value of 0. Since the turns alternate between the players, one player will always have a move with a Grundy value of 0, and as long as he plays one of these moves, he will again have a 0 Grundy value move on his next turn. One of the main implications of Sprout-Grundy theorem is that assuming both players are playing optimally, the game's outcome is predictable even before the first piece is played, as with symmetric play. This means that there is a winning strategy from any game state, regardless of the size of the board. One of the players is guaranteed a win from any game state, assuming that he plays the right move on each turn. That is, he must always play a move with a Grundy value of 0. This can be better illustrated by envisioning a tree for all the possible moves in that game state. A 0 Grundy value implies that on the next turn, all possible moves will put the game in a state with a non-zero Grundy value. The player who first played the move with a Grundy value of 0 will always have a move with a Grundy value of 0 on his next turn. However, if instead of playing a move with a 0 Grundy value, he plays one that is non-zero instead, then his opponent will have moves with a Grundy value of 0, and can take the game from there. As long as one player always plays moves with a Grundy value of 0, he is guaranteed a win. These are some of the known Grundy values for empty Cram boards of various sizes. The player who first played the move with a Grundy value of 0 will always have a move with a Grundy value of 0 on his next turn. The even by even boards will always have a Grundy value of 0, and the even by odd boards will always have a non-zero Grundy value. This means that on even by even boards, the second player always wins, and on even by odd boards, the first player always wins. In conclusion, there will always be a winning strategy for any game of Cram. This is in agreement with what we have found using the symmetric play strategy. The odd by odd boards do not show any noticeable pattern.